All right, welcome everybody. So in the next set of videos, we're going to walk through working with determinants more, and in particular, working through some properties that this new operation that we've been talking about, determinants, satisfy. So we can think of a determinant as a map, as an operation on a matrix. So we input a matrix into this determinant operation, and out comes a scalar number. And we've seen that scalar number has some implications relating to inverses of matrices. And relating to inverse matrices, one way of finding an inverse matrix is to apply elementary row operations so that we can take that original matrix and express it in its reduced row echelon form. So maybe there's going to be some connection that we can make between this determinant operation and elementary row operations that we apply to a matrix. So this first slide is going to point out three really important properties. So the first property is relating to the row replacement operation. And so if we apply a row replacement to some matrix A and that produces some matrix B, then those two matrices A and B will have the same determinant. In other words, applying a row replacement operation to a matrix does not affect the determinant of the resulting matrix. For a scaling operation, that is going to affect the determinant in a way that you probably might expect. So if I apply a scaling of one row of matrix A by a factor of k, so we're going to multiply one row of the matrix A by some scalar k, and that gives us matrix B, then the determinant of this new matrix B is going to equal that scalar k times the determinant of the original matrix A. So scaling by a factor, one row by a factor of k, also scales the determinant by that factor of k. And the third bullet here says that if we obtain matrix B by performing an interchange of two rows on matrix A, then the determinant of this new matrix, which had a couple of rows interchanged, is going to be the opposite sign as the determinant of A. So it's going to change the sign of the determinant of the original matrix A. And so let's investigate why each of these properties is true. And let's start with this second bullet, which is the scaling operation. So we'll prove this in the space below. So let's consider matrix A, which is an n by n matrix. And B is going to denote the matrix that we get when we multiply the ith row of matrix A by the scalar k. And so for example, if we had a 3 by 3 matrix A that I've written out over here, and we were to multiply the second row by this scalar k to get matrix B, then matrix B would look like this. So let's see what happens now if we try and take the determinant of the resulting matrix B that we get. And we're going to do this by performing a cofactor expansion across row I. So we're going to go across the row that we just multiplied by this scalar. So if I do a cofactor expansion across this ith row, so for example, in this 3 by 3 case that we have here, if I did the cofactor expansion along with the second row is the row we multiplied by k, then I would get a minus B21, right? Because the sum of the 2 and the 1 is 3, which is odd. So we put a negative sign in front of that, and then we're going to multiply. I'm just shorthanding the notation here, but the determinant of the corresponding matrix that we get when we eliminate the second row and the first column of this matrix. So that's getting rid of this. What's left is A12, A13, A32, and A33. So we would take the determinant of this, and then we're going to add to that B22, which would be this entry right here, times that matrix that we get when we cross off the second column and the second row. And then we're going to subtract, because 2 plus 3 is odd, B23 times the determinant of the matrix we get when we cross off the third column and the second row. So in general, we could write that out like this. So Bij, that's representing each of these coefficients across the row. So we're going to sum over each column, and Cij with the B over here, this is denoting the ij cofactor. So remember, this cofactor is telling us the derivative of that matrix, and it's also sucking up whatever the sign might be that we attach to that determinant. So we would just write this as the sum of the Bij entry times the cofactor, the Ij cofactor. So that's a little bit of a review about those cofactors. So in this case, we can see each of these Bij's is going to be K times Aij, right? We're just multiplying the corresponding entry in that ith row by K. So we can replace each of these Bij's with this scalar K times Aij. And since we haven't changed any of the other rows in matrix B, all of the other rows in matrix B are identical to the rows in matrix A. All of these cofactors for matrix B are identical to the cofactors for A. So these are the same, and Bij is equal to this scalar K times Aij, because that's all we did to get matrix B was multiply the ith row of matrix A by K. And now we're going to sum over J. So this scalar K is independent of our sum. So we can pull that out from inside the sum, and that's why that is out over here. And now what's left over, this expression in green, right, is exactly the cofactor expansion along the ith row of matrix A. So this is exactly the determinant of matrix A, and that is what we wanted to show. That determinant of matrix B, the one that we get after we multiply one of the rows of matrix A by this scalar K, is going to equal K times the determinant of that initial matrix A. So we'll take a look at these other properties on the next couple of slides.